It's
Hi,
5 minutes.
All
right.
Actually.
Good afternoon, everyone. I'm stepping in as host for Susan just for this week.
Okay.
And unfortunately, she asked me to come in when my good friend Ben is presenting. So Ben Wang is from Lawrence Berkeley National Lab. He's a research scientist there. Does a bunch of work on, well, you're about to find out, but electric vehicles and charging infrastructure and yeah, maybe you could even before, I don't know if you already have slides on this, but maybe tell them a little bit about your sort of background and how you came to do this work.
Yeah, sure. I don't
How
have.
can they all get hired by you?
Yes.
Yeah, it's not a guarantee. But through the early talks just now, I'm really impressed by the broadness and depths of the knowledge the folks have at the UC Davis Transportation Research Group. My name is Wang. I'm a research scientist at Lawrence Berkeley National Lab. This is my 10th year as Berkeley Lab employee, starting as a postdoc in 2016. And right now, as a scientist, my research interests have been centering around the electric trucks and infrastructure analysis. But before I joined Berkeley Lab, I started my journey in UCLA, Smart Grid Energy Research Center, to develop a lot of charging algorithms, control algorithms for the electric vehicles that have been deployed in the real world on UCLA campus. And there are a couple of microgrid related projects where I founded my PhD journey. And in this HEVI-LOAD project, started a couple of years ago, sponsored by CEC. We start to look at the charging infrastructure needs by these emerging sectors and where the chargers need to be deployed, what type of chargers, that type of question. So overall, this is how I evolved into where I am right now. And very happy to give a talk on our recent study on the national scale truck electrification analysis, which is a really big project with so many different aspects. But what I'm focusing on right now is using the HEVI-LOAD tool to analyze truck charging demand at the national scale with different geographical resolutions. It's a very interesting timing to talk about this issue, as the electrification trend and momentum may have some various news, but still the focus I want to share with you guys is more on the research side, the methodologies to set up the scenario and make it running at the national scale. So at the end of this talk, I want folks to be familiar with the modeling approaches and the big takeaways from the national study, including the load shapes, sensitivities with respect to a number of key parameters, what we developed as a key knobs under the hood that drives different load shapes. And then hopefully that will spark some ideas more on the collaboration in the future. So that's my lengthy self-introduction. With this, we can start diving into the talk today. Yeah, any questions before we start? Okay. Yeah. So first, I want to appreciate the collaborators along the way in the HEVI-LOAD projects, as you can see on the screen. This project was initially sponsored by California Energy Commission, starting from some of the key research capabilities at Berkeley Lab, like high performance computing, big data analytics, etc. Then we use this capability to build the transportation scenario for California to answer a couple of key questions needed for the AB 2127. And right now, we are also trying to help with the Senate Bill 643. And later on, we grow this project portfolio and capabilities to support the national scale study that was used to support the multi-state transportation electrification impact study, which is the TEIS study right here. In this study, Berkeley Lab played the role to analyze the heavy-duty sector for trucks from class 4 to class 8. And our partner, National Renewable Energy Research Lab and Kabbalah, they work on the light duty and the grid impact analysis respectively. There are also a couple of regional demonstration projects. We use this tool to engage, ranging from the transit charging control to regional planning projects for different corridors in the state. For example, we have ongoing one to have a microscopic view of the I-80 connecting Port of Oakland and the state of Nevada. So really appreciate it. I think we can leverage this, existing capabilities to answer more questions in the future, and we hope to make it as an open platform that folks can, deploy more interesting ideas, not only for your research problems for PhD journeys, but also for answering bigger questions for the societal benefits. Okay. So this study was about the answer to EPA's request as a client request to DOE to help them answer the cost and infrastructure needs before they implement the heavy-duty rulemaking last year. So there are a couple of questions from them. For example, the notorious location-specific questions about infrastructure, where the chargers are needed, what type of chargers are needed at that particular location, will drive the cost problem quite differently. And what's the grid side requirements for integrating this amount of electric vehicles in the future? So that's why the capabilities within the DOE warehouse were assembled together to help this analysis. How the study was set up was showing on this slide. We took the scenarios from EPA directly, including the action scenario and also the reference scenario or non-action scenario. The reference scenario aligns with a couple of existing statewide initiatives like Advanced Clean Truck in California and some other states endorsing the ACT at the national scale. And also there are other concerns in the EPA adoption scenario when they create the action scenario where it's a little bit more aggressive. For the heavy duty sector, the action scenario has more than doubled population of electric trucks in the study. Emerald and Berkeley Lab using their tools project the load shapes as at regional and the location specific levels, and the Kabbalah take these load shapes in a downstream analysis by mapping the load shapes on those specific circuits to the 5 selected states, including California, Oklahoma, Illinois, New York, and Pennsylvania. However, even though the study was the result was for 5 states, in terms of the transportation modeling, we have to cover the entire nation. As I can show later in the slides, the trips and routes are quite intertwined. If you are looking at one specific state, that may involve the trips coming from other states that just stop by these particular states, creating in-route charging demand. So that's why we had a topic about national analysis. How we're gonna do it is showing on this slide. This slide, we made for the methodology, not only for the national study, but also for the CEC's AB 2127 study. Overall, the workflow starts from the left-hand side diagram here, I would say the most important input into the heavy load model is the travel demand model. As you can see, those arcs connecting different points on the map. Travel demand model is essentially statistical model that tell us how many trips are coming from different locations as trip origins to other locations as trip destinations. Right, it's a statistical distribution that matches the real world data we've seen from different telematics data set. Even this travel demand model was calibrated with different real world location data in terms of starting time, trip distance, parking duration, etc., just to make sure that synthesize the universe we have resemble the real world. And also, according to the different adoption scenarios, we have the zero emission vehicle stock, and the different types are mapped to different powertrain types, battery sizes, and other vehicle specifications. All this stuff harmonized serves as an input to the second, which is a backbone of the heavy load tool, which is agent-based simulation. What it does is to keep track of every activity or every vehicle in a simulated environment, where it starts, where it's going to, time, from minute to minute resolution, and we want to keep track of the integrated driving, parking, and charging activity, so that we can log these events for the post process into different geographical regions. We can show the results, as you can see, to the county level, corridor level, or specific location level. The way we did this was by treating the locations explicitly in the simulation, so that they can be selected by particular trips as the en-route locations or as the trip starting locations, like the depot, truck depot. If we dive into the specific location, the load shapes can be reviewed by aggregating the charging events together. This is a location level analysis to inform, site developer or fleet operators, decisions. Later on, we're going to see more detailed examples at the location level. But at the state level or high level, we can try different what-if scenarios on the behavior or on the infrastructure assumptions, so that the aggregated results can be in showing in different fashion.
Can you just, I'm going to ask you, the GPS data, how does that, are you going to explain how you use that? Or you can tell us now, where does that fit into the picture? Because that would be very high resolution data, and where do you get that GPS data from, the truck GPS data?
Yeah, for the truck GPS data, there are a couple of sources. One is the UC Riverside data that recorded the 90-ish trucks and their operations second by second. That's one source that we can review the type of trucks behavior or duty cycles from time to time. The second data source was the West Virginia University data set. Similarly, second by second resolution. Those two data sets were originally funded by CDC. And we really appreciate their sharing of this data set. And then there's an INRIX data set at the national scale. And also this fleet DNA data as well.
So it tells you something about the duty cycles. Does it also tell you actual, like, where vehicles are moving around on highways? Okay, so you're using it at that level of detail. Okay.
Right. The truck volume aggregated at the corridor level was mostly used as a calibration source. We are more interested in the origin and destinations, because we want a map to different routing strategies we have and in this software, instead of relying on their trajectories. Evolving from the statewide study to the national scale, as you can tell, the methodologies share similar backbones, but the travel demand model gets more complicated. There are a number of more data sets we took advantage of in the DOE space, as you can see, the MHTS truck OD data, rate analysis framework data, experience registration data, etc. Also, all this data will fused in a way to inform the travel demand model. As you can tell, as I mentioned earlier, the routes are quite intertwined for multiple states. For example, the green routes are the route that start from the New York State and into the New York State directly, but the red ones are those just passing by. So it's hard to focus on only one state for the results because there are maybe emissions and energy demand carried over from other parts of the demand from the trips. We can talk more about the methodologies, but the output of the national study is the charging load projection at the county level. You can distinguish the result by the type of load chargers, like depot chargers, public in-route chargers, etc. It's based on the different definition of the charger and also location. Specifically, the truck OD data from INRIX that was used as a sampling seed. As you can tell, on the map, there's origin and destination where we can process them as a geographical distributions. And then a bunch of other data was used to augment this synthesis process. Eventually, it's a sampling process. We draw trip OD samples out of the travel demand model and come back to compare with the given scenario from EPA. Because the EPA scenario tells us, the total energy demand at the state level by different vehicle segments. We want to make sure the sample or synthesize the trips to share the same energy and travel statistics as the input scenario. And then at the trip level, you see our DNA and other data sets are used to calibrate the trip starting time, parking duration, and travel distance. And after that, we try to calibrate another type of parameters, which is the behavior. Behavior is something mainly driven by assumptions, like if a truck drives out of the depot in the early morning, what's our guess of the startup charge? So we have to rely on some of the real world truck deployment or testing data set to keep track of their starting SOCs and use that as a starting point to calibrate the trips we synthesize. And eventually, those locations, as you can see here, are from the JSON's law database with about 2,800 truck stops and rest areas at the national scale. This is not the complete database of locations where a truck can park, but that serves as the initial guess of candidate locations. So that's a data set under the hood that we use to calibrate the study. And in terms of output, there are different types of output, as you can see. We can see the location level load shapes, or we can zoom into a particular location to see how the loads from different vehicle types or charger types stack up. And we can also evaluate the aggregated statistics for example, in this particular case, the long haul tractors versus short haul versus vocational. We can also see the simulated truck volume aggregated to the freight corridors that was used to harmonize with other freight corridor strategies to see if the same urban congested corridors can be prioritized from different data sets. The public and depot charging load can also be visualized to different geographical units depending on if it's a location specific study or census block level or county level. So overall, it's quite flexible to tell us so many different things as we try to make this whole platform as a fancy calculator where you can turn different kinds of knobs to drive to different results as output. But more importantly, we want to build some sensitivity analysis pipeline so that you understand the impact of or change of one particular results with respect to certain key parameters for the knobs being turned under the hood. So overall, this high level methodology overview, particularly here, as Lou mentioned, there are a couple vehicle types in the data set we extracted. Each one has quite different start time distribution and end time distribution. So sort of resonates to the argument that medium heavy duty space is really complex and has so many heterogeneous behavioral patterns. Statistical approach is what we took to accommodate different vehicle behaviors and duty cycles in the simulation. We believe it's so far has a good coverage of the vehicle types, but it's a very challenging task to cover the 100% duty types of duty cycles so far. So far, the effort is really trying to push to the last mile of this modeling practice.
What's the difference between the left side and the right side?
The left side is the distribution of start time and end time, and the right side is the trip duration. The how long the trip is from when the trip starts to the trip ends, and also when the vehicle is parking there, how long is usually the duration, labeled as trip intervals.
So this doesn't include long haul trucks, looks like.
Yeah, those are selected vehicle types just to match the same number of rows.
I mean, do you have long haul trucks that run 24 hours a day or 20 hours a day? I mean, I think there are some, right, with multiple drivers.
Yeah, this is a great question that's roughly reflected in the load shapes by this long haul sector, which I will talk about that later. One particular knob in the simulation is how we treated the location types. We assume the starting location and ending location of trips are the depot locations, where the locations the trips will most likely charge before the trip or after the trip is finished. But the second type of location, besides the depots, are the public locations. In this study particularly, we focus on the public in-route location. Suppose a truck just running on a road segment and just realizing the battery is dropping low, below like 30%, for example, that triggers range anxiety. The truck drivers start scanning in the direction of its originally planned routes, and wondering what is the best location to stop by and charge, right? So here, how the best should be defined is a research question, but here we choose the total distance as a metric to for the decision criteria. That means the truck trip at this particular moment will be broken into two parts, from the current location to the selected charger, and then from the selected charger to the original destination. However, there could be many chargers as candidates in this case, and even after trucks select the first charger, there are subsequent chargers that may need to be selected, because the long haul trips covering the whole country may need multiple charges during one trip. So we made this function recursive, so that any vehicle can adaptively select the en-route locations in the simulation on the fly. So it's another critical mechanism we developed that can enable the location specific analysis. Yeah, any questions about the, bolts and nuts under the hood? Okay, great. And then there are some, lobe shape results, which are, required by a lot of, utility industries. For example, what's the load growth in my territory in terms of the peak power or the total energy demand per day? So as you can tell, given the EPA scenario, we have the 2030 to 2040 load growth. And in the vertical direction, we can also see the load shapes from national scale and then zoom into the state level and then zoom into a particular county. One interesting question, if you notice, is that we have a little peak for the national load shape around 9 p.m. or so. That was an interesting point for us to investigate a couple months ago, why there is a tilting point. But then we realized, United States has a really large geographical scale. The charging load from the New York on the East Coast have quite different load shapes than that in the California. So aggregated together, we'll see that type of bell shape around 9 p.m. The other question is, if we zoom in as granular geographical scales into the county, the load shapes becomes more spiky, right? And we dig into the data set and investigate the load shapes or charging events that created the load shapes, and we find out that a lot of peaks cancel each other out at the larger scale. But in the small scale, the load shapes are driven by this random charging behaviors with different charging powers. And this issue becomes more severe if we look at the location level results. On the right-hand side, are the aggregated the daily energy demand and the peak load at the county level. At the first glance, it aligns pretty well with the urban centers of the United States, like California area and some, metropolitan center. And also for some locations with high demand, if we connect them, in a way which really aligned with the freight corridors, those areas. That means the charging load we simulated, consisting of the depot load and the public charging load, are driven by the freight demand along the freeway corridors. The other interesting maybe issue is that for the California counties on the West Coast, the geospatial scale is really large. That makes it hard to compare, on the density perspective. But aggregatedly, some counties like San Bernardino County, Los Angeles County, right? They showed really huge aggregated energy demand. But if you zoom into a specific, census block level, that may not be the case. So that's one issue we are trying to solve using even more granular geographical units like a census block instead of counties. Yeah. This plot showing pretty much the same thing as a previous one, but in terms of the vehicle types instead of the charging power. You can see the relatively heavy-duty Class A long-haul trucks consumes significant amount of energy within all sectors, which is the yellow part in the higher level visualization. And the long-haul application, which is a Class A long-haul, showing in the blue, kind of shows a relatively, stable load shapes with the peaks and valleys, closer than other, segments. However, there are still, some, higher levels during the night, versus, higher levels, in the early morning versus during the night. That was because the, trip starting time we have seen in the real world database showed us a lot of trips starting like in the early time.
Looks like you're getting a lot more charge demand from short haul than long haul.
Yep.
Interesting. Because in the diesel world, long haul demands a lot more energy than short haul.
Yeah, short haul was defined with the operation radius as 250 miles.
Yeah.
So they serve more to the regional business needs rather than the long haul, freight transportation.
Are there different rates of electrification for those two kinds of trucks? Like, is there a higher rate for the short haul?
Yeah.
Okay.
And in the lower level, those are the load shapes aggregated by different power levels again, from US to San Bernardino County. You can see that 150 DC charger contribute to most of the load, in the stack plot, which is different from the previous results we provided to California. Because in this study particularly, the one interest from the sponsor is to look at the cost effectiveness of the charging infrastructure, while we bring in the economy of scale factor that assumes mass production of one particular charger type will reduce the cost significantly. So a lot of people charging sessions will map to this 150 chargers. We hope that through this approach the cost can be reduced in some way. And this slide shows some sensitivity analysis. As I mentioned earlier, if we assume the SOCs in the truck's battery resembles the real world data we are seeing today, we labeled it as the base case, and we generate the charging load shapes for the public versus depot. However, if this SOC distribution changes a little bit to different directions, we want to know how this will impact the load shapes and also the percentage between the public charging versus the private charging. So we did additional two cases. One is a high case. High case means that we increase the SOC distributions to the high end. Like if, for example, if the previous SOC average SOC value is 80%, now it's getting to 90%. But it's a higher. That means vehicles have more energy in the battery to start the daily job. And we find in this case, originally we have seen some charging load here, but now it gets shifted to later into the night. And particularly this is for the orange one. Orange one is the public charging. This sort of aligns with our expectation that if the truck needs some charging just in time during its trip, right, it's gonna look for the in-route charging and stop by charging accordingly. But in this case, if all the trucks have higher starting SOC before they start the trip, it's less likely for them to search for the in-route charging stations. It's less likely for them to trigger the range anxiety, which was defined as 30% SOC in this case particularly. Yeah, so
There's a question here.
Sorry, could you explain what SOC is again?
SOC is the state of charge.
So how much?
Indicating the percentage of energy left in the battery.
at the start of the trip.
Third case is that we totally randomize the starting SOC, make it like a average as 50%. So you can see the charging demand on the public side is significantly boosted. There's one case on the sensitivity analysis. The other one on the at the location level, at the first glance is very chaotic, right? As we supply multiple type of chargers to this location, particularly ranging from L2 to DC, 1.5 megawatt charging station. Right, there are 1.5 kilowatt as a maximal charging power is the base case in this sensitivity analysis. We want to see what's the load shape looking like if we increase the 1.5 to 3 or reduce the 1.5 to 500 kilowatt. So that's the base case, a high case, and a low case corresponding. For the low case, of course, you see less needles per location, and even though the total energy amount equals the other two, but the site level peak load is reduced. But if you look at the high case versus the base case, surprisingly, the needles do not overlap with each other to a much higher value, right? Our expectation is that if you have multiple megawatt charging sections for a location, you're gonna see a much higher location level load. However, it's not the case because we realize those charging sections have very likely to have the mismatch of the starting time. They will not stack up with each other very easily. Even though you increase the charging power per station, at the site level, still, the peak load still remain the similar patterns. As I said, even though we reduce the peak charging power to 500 kilowatt, it reduced, but it's not reduced so significantly because for lower power charging stations, we see more chance of them stacking up with each other. So the other case study is that, how about we take the circuit capacity or how about we take the energy percentage to the high power charger as a variable. For example, at the site level, by tuning the charging vehicle type, we want to make sure, for example, in the high case, we want to make sure 30% of the energy to be consumed by the megawatt charging station. And we can even go further to 50%, make sure 50% of the energy to be consumed by the megawatt charging. And you can see, the things don't change very dramatically due to the reason I mentioned, this megawatt charging is supposed to make the charging cycle very short and very fast, and less stacking effect. From the violin flow down the left, the peak power for the high case even reduced a little bit from the base case. So all this points to the conclusion that megawatt charging is less harmful than what we expected earlier. But another question is that even though it's less harmful, but the ramping up of the load instantaneously can still be an issue to the utility companies. That calls for other solutions like on-site battery storage or other managed charging solutions, just to reduce the ramping up, ramping down frequency issue. Yes.
What do you mean by harmful?
Harmful is from the utility perspective. If you have, for in this case, 14 megawatt charging load ramping up in like a couple of seconds, it's like it's very likely exceeding the circuit capacity, or if all these sites working together, they probably need to call additional generator to compensate this instantaneous load.
Do you assume the batteries can handle anything? Because right now, a lot of I think almost all trucks on the road the battery systems would not even allow that, right? They're governed for much slower ups and downs, and even if you have a 1 megawatt charger, I think it's not gonna take anywhere near full advantage of it. But are you just assuming we get through that and these batteries can do anything?
That's a great question. We're just pointing to the potential solution using battery storage on site to buffer these instantaneous peaks. But to what degree the battery packs can 100% follow the ramping up rate is still a question. Essentially, this charging power, even at the megawatt charging station, is the power absorbed by the vehicle battery, right? It's a type of battery. But on the location side, the stationary battery can still perform similarly as a vehicle battery. Is an assumption. One caveat of this approach is that we're just counting or calculating the load shapes naively. This is the total energy by X kilowatt hour, and then we just distribute that, X this amount of energy into the time segments to generate the average charging load curve. One thing we are working on right now is to incorporate the power electronics constraints on the grid side and the battery chemistry on the vehicle side. So you will see very interesting phenomena for each one of these charging events. It's gonna shoot up early, but as the SOC increases rapidly, it keeps dropping to a level that what we mentioned as the last mileage delivery of the energy could take longer, much longer than the first 20%, 30%. But still, from 20% to 80%, can be much faster using the megawatt charging system. This is just the last 20%. May be very slow.
And maybe drivers won't want to wait around for that anyway, right? They'll go out, they'll leave at 80%.
That's a question not only for drivers but also for the fleet operators. Do you want your fleets to charge the last 20%? Right? Operationally, it's gonna cost a lot of time, loss of efficiency for your fleets.
Is there actually data on the charge curves, or are you like, how are you assuming what the charge curves look like?
Yeah, this is a great question. There is a website, hosted by enthusiasts in the European countries. They measure the charging power curve for their vehicles. There are about like 20 to 30 types of EVs. We had this little collaboration with UC Berkeley, Scott Morris group, trying to model the charging curve at the cell level, C rate versus the SOP, so that we can map to a larger battery pack, theoretically using the historical data. So, because the heavy load has really granular charging events simulated. When the vehicle enters the parking garage, we know the arriving SOC and the charging power mapped to this vehicle. So second by second we can track the power curve. So it's one thing we have very preliminary results on. But one thing I can say, it's gonna significantly change the load shape at the location level. Any questions? Okay, hydrogen, I'm gonna go a little bit faster, because this is very preliminary and we're still trying to finalize it. In the EPA project, we also mapped their hydrogen fuel cell adoption scenario into the heavy load simulation. But the assumption is quite different from the battery electric vehicles, without assuming the depot charging, because we are assuming it's hard for every fleet to install hydrogen refueling dispensers in their backyard. So the public in-route charging at nearby depots are the dominant location types. So you can see the simulated refueling demand aggregated to those truck stop locations, as shown on this animation. There's some demand showing up on the East Coast in the early morning, and you can see those dots, proportional to the charging demand at each location, and the shifted to the West Coast, and there's another practice to aggregate this demand at individual locations together into one larger location. This leverages some of Yanning's work to do the optimization based on the volume of trips, the location spacing, and total energy demand at each location. So that if we use a 200 mile as a constraint, to space out the locations, the larger green dots are the results. If we use the 300 miles, the blue dots are results. So you can see how this locations locations show up on the map geographically.
Is the size of the dot the size of the station?
Size of the demand.
Demand.
It's not necessarily the number or type of stations yet. We just try to aggregate the demand.
Okay.
As we develop more functionalities within HEVI-LOAD, some of key directions here for discussion. One direction is to extend the vehicle travel from trip-based to tour-based. In the national scale simulation, we are using each individual trip to represent a vehicle, which is a caveat as well. Right now, we're using more granular telematic data from INRIGS to keep track of every vehicle's behavior. One vehicle can have multiple trips over multiple days, making it more realistic, but also more challenging to design the charging infrastructure and the charging decisions. And also different location types supplied to these models. We want to make sure the warehouses, public destination, nearby depots, these notions are well covered in the new location definition. There's some preliminary results we are doing for HEVI-2127 using different numbers of locations. And on the public side, on the left are the 300-ish parking locations from Caltrans California statewide truck parking study, and then the 1,000 locations from CalStar's survey as an input. So temporally and geographically, the load shows quite different patterns. The other thing we are actively developing is a managed charging strategy. We have very heuristic method in the TI study by heuristically, reducing the power for the selected depot charging sessions, right? Where you can see that, red curve has lower peaks, but it's still not very effective. And then we have this optimization-based approach, assuming every charging session is controllable. So we can see the green curves. For the green curves, you can achieve a very flat load curve in these cases. So this is a ongoing process and a lot of interest from many agencies for us to dig into this. So still early, but we'll have more to share with folks. So this slide concludes my presentation. It's more on the methodology sharing side. But happy to discuss if you have any questions.
Right, questions?
Thank you for the presentation. I was gonna ask, from a planning and infrastructure point of view, how could you see, I guess, this infrastructure potentially being, I guess, dictated or not dictated, but kind of driven by plans or policy from the state level or CTC or Caltrans or something?
Yeah, that's a great question. And it's like on the adoption side, there are different angles to think about how many vehicles there will be in future. One, as you said, policy or regulations as a driving factor. The other factor is the economics. As we have seen some real fleets adopting electric trucks having really low OPEX. OPEX means the operation and maintenance cost, right? On the other hand, the initial investment in a lot of cases is very daunting as a barrier for adoption. In here, we would like to take a balanced approach. For this California study, we're taking the AAT3 adoption scenario as an input. For other studies, for example, this one, the EPA's adoption scenarios, we use that as an input. This scenarios, in my opinion, are a combination of the economics-driven adoption approach plus the regulations. Thank you.
Okay, so can we jump back to the last slide about the man charging here? Yeah, so I'm not sure like if this question is okay. So you mentioned like you're using the optimization methods for the man charging, right? And I see like in the last sector for the green line, it's so flat. So can you tell us like what kind of scenarios are you, or what kind of constraints are you using like for the theoretical optimization methods to come to that, kind of flat result in the end?
Okay. Yeah, that's a great question. It's also, the limitation of the study of being purely driven by optimization versus more, driven by realities. The optimization problem was framed with the objective to reduce the peak and also minimize the fluctuation. So the peak as one term, and then as another weighted term to reflect the the norm of the curve. Constraints, the fluctuation is actually by aiding the simulated charging demand on top of the assumed circuit base load, because we are assuming this on commercial circuit. So that's why the load added on top of the base load as a new load. So we form this optimization, and also this assumes all the charging sections are open to be controlled exactly when they start, how much power they can charge, right? So you can see the algorithm actually is very aggressive, right, to control them to behave as flat as possible.
I think there was a question online. Let's see. Yeah, okay, are there any plans to expand the model from US only to a North America model, like US plus Canada? And then they're saying, for context, there's similar research being pursued at Canman Energy Research Center as part of the Canadian government in Ottawa.
Yeah, thanks for the question. So far, there's no plan for us to cover Canada in this model, but technically it is feasible if there's a strong interest or request from Canada agencies. Similarly, in another conversation with Delft University in Europe, they are trying to leverage some of this work to develop infrastructure planning network in another continent. So there are interests from us, but there needs to be push or momentum, either from Canada or from Europe to establish this collaboration, and we are open to it. Looking forward to it.
Have you seen any changes in the charging behavior and demand load from East Coast to the West Coast?
There could be charging demand, difference, but we haven't investigated yet. The reason I'm saying is that we see the travel pattern difference. So naturalistically, the charging behaviors are driven by the travel behaviors. And this question is great also as it relevance to the behavior change after electrification, like how the fleets will behave after electrification compared with the traditional diesel fleets, right?
How would you describe the difference in travel behavior between like East and West Coast or different regions that you just mentioned?
There are a couple of metrics we care, like the trip starting time, trip duration, distance, parking duration, etc. Those are from the telematics data set. But beyond that, we are also interested in the payload patterns. Because the payload, which is another caveat, so many caveats of this study. One caveat is the payload factor is, we are using the average payload in this case. But according to some statistics, like more than 30% of the trips running on the road are empty. That will make the energy, consumption rate quite different in terms of kilowatt hour.
Any other questions? I have a quick question. I'm trying to remember, but can you describe how in the trip one, not the tour one, how are you deciding on nodes? Because I know so the depots and the ODs, that I think that's obvious, but then how are you essentially deciding on where the nodes are located?
Yeah, that's a great question, which bothered us for quite some time. It's a question about location definition, given the GPS location data. I can go back to locations. Yeah, the red ones in this visualization are the in-route location. By the freeway, we can, from the satellite image, we can see those are the truck stops. And there's assumption that in the future they can be accessed by the public. There's also another type of public locations that have so many different fleets visit on daily basis, and their locations are near the urban areas, and we classify it as a public destination. It's a public location, but it's not in the freeway area, and many other fleets can share this location. There are also locations dedicated by certain fleets, and they align with the warehouse data, and they align with some fleet survey data. So we label those locations as depot locations.
It's a lot of work.
anyone else? All right, well, yeah, thank you very much.